Hello, everyone. Welcome to Pre-Lecture 20. This is going to be the start of Chapter 15 for us, looking at solubility equilibria. Okay. So if you recall from Gen Chem 1, the solubility of a substance can vary depending on what it is, of course. The solubility can be essentially zero, that it wouldn't dissolve at all, something we would call insoluble, or it could be sparingly soluble, or if something is fully miscible, if we think of like sodium chloride, I guess that will certainly have a saturation point, but we could have up to infinity solubility with something like methanol dissolving in water. Oftentimes those are liquids dissolving in other liquids. But what we're going to focus on this chapter is primarily solids with sparingly soluble. So an example we have here is silver chloride. That is a solid, and it is going to partially dissolve in water. And so if we look at our beaker representation down here, we have solid sodium chloride, and then it will partially dissociate. So some of our silver will come off, some of our chloride will come off, but most of it will remain as a solid that is insoluble in our water. Okay? And so we can, of course, define this relationship in terms of equilibrium. This is another form of equilibrium we'll look at called the solubility product. And so we represent that with KSP. So if you see KSP, that is measuring the solubility of a solid within a system. And so for this example, we would write our KSP like we do for all of our K expressions with our products over our reactants. In this case, our products are silver, Ag+, and chloride, Cl-. Then our reactant is silver chloride, which is a solid. And as a reminder, we don't need to include solids or liquids in our equilibrium expressions. So we would just say KSP is equal to silver times chloride and the concentration of each of those. So take a minute here, and here are a couple practice problems. So go ahead and try these out. Write the KSP expressions for the solids magnesium hydroxide and calcium phosphate hydroxide. And so if you want to take a second to do that, you can pause the video, but I'm going to go ahead and start doing it. So if we write the equilibrium expressions for each of these, or rather the chemical equations, we have magnesium hydroxide, and it will be in equilibrium. Sorry, this is a solid, I should say. And it will be in equilibrium with its dissolved ions, which are, of course, Mg2+, which is aqueous. And then it's hydroxide, which, oops, before I write the O there, we would want to include the stoichiometry, of course. So we get 2 hydroxide ions for every magnesium hydroxide that dissolves. So if we write our products over our reactants raised to the stoichiometric powers, KSP is equal to our concentration of magnesium, Mg2+, raised to the first power, and then hydroxide minus, and we would square that concentration because of our stoichiometric coefficient of 2 for our hydroxide. Okay? If we have our calcium phosphate hydroxide. So calcium phosphate hydroxide is actually a mineral that is called calcitite. And this is actually what your teeth are made out of. So, or at least the enamel in your teeth. And so if you ever go to the dentist and they say, you need to protect your enamel, this is what you're actually protecting. Of course, it can dissolve, so you can have teeth degradation. And so this would be the process of your teeth dissolving, which is just lovely to think about, I'm sure. But anyhow, the chemical reaction for calcium phosphate hydroxide, again, this is a solid. Sorry, I should have labeled that. We will get calcium 2+, and so Ca2+. We would get 5 of those. Sorry for my weird looking 5 there. 5 Ca2+, that would be dissolved, plus 3 of our phosphate ion, so PO4 3-. And then we would get 1 hydroxide as well. And so if we wrote the KSP expression, the phosphate and the hydroxide are also aqueous. Sorry, I've been a little lazy on labeling my states here. Our KSP expression is going to be equal to concentration of calcium to the 5th power times our concentration of phosphate, PO4 3 minus, to the 3rd power times hydroxide to the 1st power. And so we wouldn't need to label that. So those would be our KSP expressions for these two solids. Okay. I'm going to keep moving on. And so we can talk about our solubility product of a slightly soluble ionic compound in terms of its solubility as well. And so if we had this sparingly soluble salt, we can of course measure those concentrations of the dissolved ions and relate that back to solubility. And so the KSP value can ultimately be determined from the equilibrium concentrations in molarity, or we could, of course, do vice versa. If we know KSP, we can determine what the solubility would be at equilibrium. Okay? So let's try an example of that. Say we have a KSP of calcium hydroxide, which is 1.3 times 10 to the minus 6. Calculate the molar solubility of calcium hydroxide. And so again, if you'd like to try this on your own, that's what I would recommend before watching me solve this. So I'd recommend pausing the video here, but I'm going to go ahead and start doing this problem. Great thing to do. I would always recommend writing the chemical reaction first. So we have calcium hydroxide, and that is a solid, and that will be in equilibrium with its dissolved ions. So we have calcium 2+, which is dissolved. And we also have 2 hydroxide molecules for each calcium hydroxide, and that will, of course, also be soluble. If we write KSP for this expression, products over reactants, but we don't need to, actually, let me erase this, write it on the side. So if we write our KSP, that is going to be equal to products over reactants, and our reactants are solids. We don't need to include those. So KSP is going to be equal to calcium 2+ to the 1st power times hydroxide squared, right? And since this is an equilibrium problem, we can solve this using an ICE chart, our favorite. So if we write ICE on the side, build our chart here, then we can fill in our squares. So again, because our reactant is a solid, we don't need to consider our reactant in our equilibrium calculations. We're going to say that we start with a concentration of 0 molar for each of our products. If we look at the change, we know that we're going to add product because we're starting with 0, and some of it will dissolve, some of our reactant will dissolve. We would say plus X for calcium, and then plus 2X for our hydroxide, because we have to factor in our stoichiometric coefficients, of course. So that would end up at equilibrium with X concentration of calcium and 2X concentration of hydroxide. So a reminder that our KSP is equal to 1.3 times 10 to the minus 6. And so if we plug all this into one equation, we should get 1.3 times 10 to the minus 6 is equal to X for our calcium and 2X for our concentration of hydroxide. And that'll be 2X squared, rather. And then if we combine some terms, our right side of the equation is going to be equal to X times 4X squared if we factor in our exponent there, which is ultimately equal to 4x cubed, right? And so if we solve algebraically, we could say x is equal to the cubed root, because we have x to the 3rd here. So the cubed root of 1.3 times 10 to the minus 6 divided by 4, which we get from the other side of our equation, of course. And so if we were to plug that into our calculator, I got a value of 7.0 times 10 to the minus 3rd molar. That would be equal to our concentration of calcium, because we have a 1:1 stoichiometric ratio. But to get our calculation of, or our quantity of hydroxide, we would need to do 2x, right, for our concentration of hydroxide at equilibrium. And so this would be equal to half of our concentration of hydroxide at equilibrium. Did not come up with that value, but if you would like me to, I of course can, and bring it up during lecture. Okay. Right, I hope that was helpful. That will conclude our pre-lecture for this class. So I hope you have a KSBS-shal day. And if you have any questions, feel free to email. Otherwise, I, of course, feel free to ask them in class as well. Have a good day, and I will see you soon.